Let's talk about PS2-0.1. This is the very first learning objective in the very first standard, all about motion. So here we can read this together, the I can statement. I can calculate the velocity or acceleration of an object using the displacement or velocity. So those, I just highlighted some of the key words we're going to have to learn to understand this. And the action that we're going to be taking is we're going to be calculating. Displacement is how far away something is from another location and in what direction. Because displacement doesn't just rely on how far away, but also where, what direction. Now let's take an example here. So in physics problems, we are often able to set a 0 point, a zero position, an origin, essentially. You know, in math class, you have the origin of a graph as 0, 0, if it's two-dimensional. If it's three-dimensional, 0, 0, 0. Here, we're going to do a one-dimensional case. So it's just going to be a single 0 point, a single origin. So relative to that origin, how far away are you is essentially what displacement is asking. And also, just like in math class, we're going to set a positive and negative direction. Now, it's up to you to set whether you want the right to be positive or the left to be positive. You could set it either way. You could do this exact problem with the left one being positive and the right side being negative. Very possible. Let's say you have a person, and this person started at the 0 location and then traveled 5 meters in the right to the right, and then 2 meters to the left. Using some basic logic, you would understand that this person would end at 3 meters away from where they started. That is what displacement is. So here, the displacement, which often in physics we use the letter x to represent, the displacement is 3 meters. Now, it's a positive 3 meters to be specific, because we are to the right, the positive direction, of where we started. Now notice in here I wrote negative 2 meters. Going from 5 to 3 is negative 2 meter displacement. So if we're just talking about from 5 to 3, there's a displacement of negative 2 meters. But if we're talking about from 0, the overall displacement is of course from 0 to 3, so that's 3 meters. That's displacement. It has a direction and a distance. Now let's talk about the distance traveled. Distance traveled is a bit different than displacement. They might sound very similar at first. But here's an example that will be a clear case of how they're different. Let's say you're traveling in a circle. Like it's a track, and you're at a track and field competition. You're doing a lap around a track. Let's say the track is 50 meters long. So that means the length of this track is 500 meters. Your distance traveled would be what you would expect, 500 meters. But your displacement, when you come all the way back around and end where you started, is 0 meters. So here the distance traveled and displacement are not the same. In fact, the only time that distance traveled and displacement would be the same is if you travel in a straight line and end. So you start somewhere, travel in a straight line, and then end. And never double back, never change your direction. Then your distance traveled and your displacement is going to be the same. That is the only case where that will be, where those two numbers will be equal to each other. Now, one thing we should specify is that distance traveled doesn't depend on the direction. And that makes sense if you think about your car's odometer. So in your car, you have something that measures how far the car has traveled. That's distance traveled. And let's say your car's odometer is reading 20,000 miles. It wouldn't make sense for this car's odometer to say it's a positive 20,000 miles or a negative 20,000 miles. That doesn't even make sense. It's just that you've traveled 20,000 miles total. The direction is not important. If your car didn't measure distance traveled, but instead measured displacement, and whenever you return back home, it would read 0. Like it's gone nowhere. But we know it's gone somewhere. So the distance traveled is telling us the length of the path, whereas displacement was telling us how far away you are from another location. Now let's talk about velocity. So velocity is how much the displacement of an object is changing per unit of time. That's the rate of change of displacement. It has an equation. This would be something to write down. In fact, let's just circle that right now. This equation right here. Now notice it's a v for velocity, but it has this bar above it. That means average. So what we're talking about here is the average velocity. So average velocity is equal to the change in position, or change in displacement, divided by the change in time. That's what that triangle is representing. That triangle is delta, it's the Greek symbol delta, and it represents change in, and it's always measured in final minus initial. Let's take another case. Let's take that we have a person, and they are going to travel a total of 30 meters. So they're going to end 30 meters away from where they started. So this is not distance traveled, but it's actually displacement. And let's say the initial time was 0, because most of the time in a physics problem, the initial time is going to be 0. Why would you start your stopwatch at anything other than 0? So a lot of times when we have this change in time, we can simply just make it time, the time it took. It's the person's initial position, initial displacement, was 0 meters. So what would be this person's average velocity if the total running time was 20 seconds? Well, here we'll plug it into the equation. The equation has a final position minus initial position divided by the final time minus initial time. Both of the initial cases were 0, so we're subtracting 0, so that doesn't do anything, so we can just get rid of it. So we just have the final position, or final displacement, divided by how long it took. So 30 meters divided by 20 seconds, which is approximately, if you round to 2 significant figures, 1.3 meters per second. Notice those are the units for velocity. So velocity has units of meters per seconds. That's the only units we're going to use in this class. Obviously, there's other units as well, like miles per hour or kilometers per hour if you're in Europe. Next, let's talk about acceleration. So acceleration is the rate of change of velocity. So just like how velocity was how much the displacement is changing per second, acceleration is how much the velocity is changing per second. So the equations look very similar to each other. The equations for average acceleration, so acceleration over a certain amount of time, the average of it, it could be higher and lower at any given time, but the average acceleration is going to be how much the velocity has changed per unit of time. So that's going to be a final velocity minus an initial velocity divided by how long that took. Let's take an example here. So in this example, a car starts at a rest. Now, let's point out that word rest. In physics, this is a very important word. What that word means is that the velocity is 0. So whenever it's at rest, its velocity is 0. Now it starts at rest. That means the initial velocity is 0. And then it accelerates to positive 35 meters per second. And the positive is very specific. And it takes the car 5 seconds to accelerate to that speed. What was the acceleration? So we're going to use our equation here. Average acceleration equals the change in velocity over the change in time. The change in velocity is the final velocity, so that's positive 35 meters per second, minus 0 divided by 5 seconds. That's going to get you 35 divided by 5 meters per second per second. That's what acceleration is. It's meters per second every second. how much are you gaining velocity every second? And velocity's units are meters per second. So it's 35 divided by 5 meters per second per second. That gives you an average acceleration of 7 meters per second squared. Now let's talk about these units. How does this work out to be meters per second squared? Well, we can imagine it's meters per second divided by seconds. And we could put the seconds over 1. That means we're dividing a fraction by another fraction, technically. So we can multiply, instead of dividing, we can multiply by the reciprocal. So we get meters per second times 1 over seconds, which gives you meters per second squared. And that is the units of acceleration. And let's go over a case where acceleration is actually going to wind up being negative. So let's take the case where we have a car moving at 20 meters a second in the right direction, which in this case we're calling right positive and left negative. Most of the time that's the case. So it's moving in the positive direction 20 meters a second. And then, after 3 seconds, it is moving in the positive direction 5 meters a second. So at no point is it ever traveling in the negative direction. It is always going to the right. It was going to the positive direction. Its velocity is always positive. But its acceleration is going to wind up being negative. So it was traveling fast and then got slow. This is what we would call deceleration. In physics, it's just another form of acceleration. Deceleration is acceleration that is causing something to slow down. So deceleration is just acceleration pointed in the opposite direction of the velocity. So the velocity is headed to the right. If the velocity is headed to the right and its acceleration is to the left, that's deceleration. So what was the acceleration for this case? Well, we use the equation. Average acceleration is equal to the change in velocity over the change in time. That's the final velocity minus the initial velocity divided by the time. The final velocity is 5 meters a second, and the initial velocity is 20 meters a second, both positive because they're going to the right. This is how we're going to get a negative acceleration, because we have our final velocity being smaller than our original velocity, which means that this top numerator here, expression on the numerator, is going to be negative because we have a small number minus a big number, and just divide it by 3 seconds. That's going to get us negative 15 meters per second divided by 3 seconds, which gives us negative 5 meters per second squared. So although the velocity was always to the right, the acceleration was to the left. Now, one thing I want to point out is that I've been using arrows this entire time. These are something called vectors in physics. Vectors have a magnitude and a direction. The magnitude is essentially just how big the vector is. So let's take the case where we have 3 different accelerations. The first acceleration is plus 20 meters per second squared to the right. And then we have plus 10 meters per second squared to the right. Now notice that plus 20 meters of the second to the right looks to be roughly twice as big as the 10 meters a second, or 10 meters per second squared. That is purposeful. These two have the same direction, but they have different lengths or different magnitudes. The magnitude is indicated by the length of the vector, length of the arrow, and it's usually relative if you can draw it to scale. Now, there will be times where we are not going to draw to scale, so all I'm looking for is whether you draw the larger vector as clearly larger than the smaller vector. Now, though both of those were going to the right, and we're going in the positive direction. But what if we had one in the negative direction? Well, then we would just flip the arrow to the point into the other direction, and then it's in the negative direction. So direction is indicated by the sign, and also just indicated by whether it's pointing to the right or pointing to the left. Now this is in 2 dimensions. Technically, we could have a vector that's pointed at an angle, and we can have vector pointing at an angle, vector pointing straight up, vector pointing to the right. We can have a vector pointed in any direction. We can even have vectors pointed out of the board or into the board, and those are how you indicate those. We're not going to use the third dimension much in this class at all, and we will very briefly use the second dimension, so we will very briefly use two-dimensional vectors when we're talking about projectile motion. Lastly, I'll leave you with a challenge problem. So in this challenge problem, we're going to have one car that is moving to the right at 20 meters per second, and then at a later time, specifically after 10 seconds, the car is moving to the left at 10 meters a second. And it's at a positive 30 meters away from where it started, which we're going to call where it started the 0 point. Now, this doesn't initially make sense, because how is it to the right but going in the negative direction? Well, that's because it must have gone past and circled back.